Okay, so hi everyone, and thanks for joining our weekly seminar. So today's speaker is Professor Rene Breton. So Rene received his PhD from the University of McGill in 2009, and he's currently a professor of astrophysics at the Jodrell Bank Center for Astrophysics, and also the head of research at the Department of Physics and Astronomy at the University of Manchester. He also holds an ERC starting grant for the study of spider binary pulsars. So his main research interests revolve around the study of pulsars, and they're used to understand extreme physics like high density matter and strong field gravity and so on and so forth. So some of his past work during his PhD enabled us to use the geodetic spin precession, a phenomenon predicted to exist in general relativity, with a double pulsar for the first time. And Rene also keeps a keen interest for science communication. And he also does a few other fun projects on the side, like, for instance, applying his skills in the area of agriculture, trying to map the spread of invasive plants using satellite imaging. So today, he's going to talk to us about spider pulsars and they're used to test fundamental physics. So Rene, thanks again for accepting our invitation, and the floor is yours.
Thanks very much, John. Hi, everyone. It's a pleasure to be talking to you today. And yeah, hopefully at some point in the future, I might swing by and pay you a visit. But yeah, I guess it's still a bit tricky. So the work I'm presenting today is basically a bit of a summary of some of the work that's been done in the last couple of years by my group at Manchester and others in the world on the topic of spider pulsars. So I've been working with a lot of people. So you can see a picture of my research group from a few years back before the pandemic, and a lot of faces have changed and new people have come in. But yeah, there's a number of people you see there: Colin Clark, Vic Dillon, Martin Franker-Quick, Mark Kennedy, Tom Marsh, Daniel Mata, Mallory Roberts, Guillaume Voisin, and many more as well, like PhD students of mine and other colleagues have also contributed to the work from my team. And then you'll see others as well, like highlighted. So the field of spider pulsars is really one that's been growing a lot in the last couple of years. So I just fetched a couple of minutes ago, actually, from EDS, searching for the topic of black widow and or redback. I'll explain what they are in a minute. So the first one was found in 1998, and then for basically the better part of 20 years, there was only maybe a small handful of papers per year, which also correlated with the number of sources known, which was basically a handful. And then around 2008 or so, something happened. And then since, like, there's been nearly a sort of exponential increase in the number of papers. So we'll see what 2021 looks like, but I'm pretty sure that there'll be quite a bit as well. So yeah, so when I started the work, I was basically a young postdoc on this topic around like the year 2000 or so, 2010 or so, and then yeah, I'm a bit older now. So yeah, so it's been about a decade. So here's the plan for my presentation. I basically want to touch on a number of topics, which is why I find these systems interesting, namely trying to measure masses of neutron stars, studying binary evolution, looking at the timing of these systems, studying radio eclipses, and then looking at the extreme irradiation. And so one of the motivating drivers, for instance, is the topic of dense matter, neutron stars. I'm sure some of you study them or other types of compact objects. they reach densities that are much beyond what we can reach on Earth, in Earth-based experiments. So the study of the sort of parameter space of temperature and chemical potential, or if you want, temperature or kinetic energy versus essentially pressure, is it's basically the phase space of the state of matter. And in sort of regular everyday life, we kind of lie at the very, very corner left, which is sort of solid, liquid, and gaseous solid state of matter. But then at higher energies or higher pressure, things become a bit different, and then usually this unlocks the very sort of particles that make up matter. So in heavy ion collisions, or such as in the at the LHC at CERN, people would slam particles at very high velocities close to the speed of light. So essentially temperatures or kinetic energy that are really high, but we're talking about very low chemical potential, because basically the particles are more or less unconfined, and we're talking about very low pressure. So therefore we kind of lie at the top left. However, neutron stars, even though their temperatures can reach a few million degrees, we're basically talking still, everything considered, about low temperatures. And however, we are talking about huge pressures. So we kind of like studying more like the bottom right area of the parameter space. And actually this region, there might be phase transitions between things like quark gluon plasma and other like special states of matter, to even maybe quark matter that we don't really know of, and we only speculate about. So neutron stars allow us to basically probe some of it, somewhat indirectly perhaps, but still. And it really relates to the very understanding of neutron stars. So since people like Oppenheimer, Volkov, and Tolman have described, the very kind of equation of state of neutron stars in the late 1930s. A lot of progress have been made, but basically a lot of it remains theoretical, because we sort of understand the main sort of constituents or parts of a neutron star, like that. We know that there should be an atmosphere, and then a crust, and then eventually a core. But for instance, at the core, we're still unclear as to whether the matter looks more like regular neutron, protons, electrons, or whether like matter is more like into a special state whereby you find like maybe pion or kaon condensates, for instance. So hopefully some of it will be unlocked, thanks to the work of people like John and some of you and my team as well, and others in the world. So just to make sure we're all on the same page, a little sort of Pulsar 101. So pulsars are a special class of neutron stars. They're the most abundant in terms of the number of neutron stars we know of. Most of them fall under the category of pulsars, which are basically highly magnetized, rapidly spinning neutron stars. So a typical neutron star would have a radius of 10, 15 kilometers, mass of about 1.5 the mass of the sun, and a sort of like typical neutron star or pulsar rather would have a magnetic field of something like 10 to the 12 Gauss. So just as a comparison, like the sort of typical magnetic field around the surface of the Earth is a fraction of 1 Gauss. So that's very highly magnetized stuff. And actually, pulsars are pretty much like the most highly magnetized objects we can find naturally in the universe, and way beyond Earth, Earth values we can reach in labs. And they also spin quickly, so between about a millisecond and a few seconds for the slowest. And the reason we call them pulsar is because the light they emit, either in the radio for the vast majority, but also we know of pulsars visible as X-ray or even gamma ray pulsars, which means they emit pulsations also at high energy, is basically somehow emitted along some sort of a cone or beamed emission at least, which is shaped by the magnetic field of the object, which is believed to be primarily dipolar. And so as this dipole rotates, the beamed emission will basically sweep across. And if you happen to be located somewhere in space where the beam sweeps, then you're going to see pulsations. So that's the basic, pulsar phenomenon. And the fact that they pulsate like that enables us to, for instance, detect dynamical motion, when they're in binaries and such. And this is what unlocks a lot of the science. So I won't expand a lot about pulsar physics because we could spend a long time about them, but that's probably about as much as you sort of need to know for today's presentation. But just so you know, like at the moment, there's something like over 3,000 pulsars that are known, and about 10% of them are in binary systems. And as they blink, you can measure the period at which they rotate. And pulsars, they naturally spin down over time. They lose energy because of for instance, the electromagnetic waves that they produce. Because you basically have like a spinning dipole in vacuum. So this should release electromagnetic waves, just according to, basic electrodynamics. And so as they spin down, we can also measure the rate at which they spin down. And these two parameters, the spin down, so which you see on the vertical axis, and the spin period, are the two main parameters really that you measure for pulsars. So many of you might be used to see, for instance, the HR or color magnitude diagram for regular stars. So in pulsar, physics, we tend to, essentially look at the period derivative versus the spin period. And you can see most pulsars, they kind of like around a few hundred milliseconds, a few seconds spin period. But then you can see also on this diagram on the lower left, there's a population there, and that seems a bit like disconnected from the rest. Most of them are surrounded by circles. The circled ones are binaries, and you can see that the binary systems are somewhere different from the rest of the population. And this is basically from the fact that if you have a binary system, eventually a companion star might start transferring mass to the compact object in an accretion disk, and this will pile up mass on the compact object like the pulsar, but also this transfers angular momentum, and therefore this means that the pulsar will start spinning faster. And so this is what we call the recycling process for pulsars. So it brings them from a few seconds, or being slow, to being rejuvenated to very fast spin periods. So typical binary pulsars, we find some around main sequence stars, as you might expect, but they tend to be difficult to detect because of, for instance, the wind of the companion star, which tends to screen the pulsar emission. So most of the binaries we find, they typically have white dwarf companions. And for instance, like, if I take the example of John's previous research, he's done a lot of very interesting research with these systems. Some, about just a bit of 1 or 2 dozen of them, have neutron stars companions, which unlocks relativistic tests. And then there's the low mass semi-degenerate objects, which is basically the topic of today, what we call the spiders. And these, they really tend to cluster at the very fastest spinning periods. So the fastest pulsars we know of, they tend to be what we call spiders. So here's a bit of spider taxonomy. So spider is basically the sort of umbrella term for these binary systems, which contain a very fast millisecond pulsar, like typically faster than 5 milliseconds spin period. They have very circular orbit and very short orbital periods. So we're talking about something like just above an hour to maybe about a day for the longest periods. And the pulsar is very energetic, and as a result, it irradiates and evaporates the companion star. So a bit like in the arachnids, like the actual black widows and redbacks spiders, where the female allegedly prey on the male after mating, and basically gets rid of it. When the first spider was discovered, the first black widow, PSR B 1957 + 20 by Fruchter et al. In 1988, it was speculated that the sort of evaporation process might get rid of the companion entirely eventually. Now it's been debated a lot, but it's still a very actual topic of research. So the black widows are the ones that were discovered first. In there, the companion is very low mass. We're talking about essentially like a brown dwarf kind of type of object. So with like masses that reach maybe a few hundredth of a solar mass. On the other hand, the redbacks, they basically look very different, very similar. There's not much difference, except for the mass, which tends to be more like something like maybe 0.2 solar mass, and above reaches maybe 0.5 solar mass for the more massive ones. And they're the systems in which we observe transitions. And I'll get back to that topic a bit later. So we can observe these systems across basically more or less like the entire electromagnetic spectrum. So in the radio, we basically see the neutron star as a radio pulsar, typically. So you see the regular blinking of the pulsar. What we observe in many systems, not all of them, but a large fraction of them, is radio eclipses. So basically, as you can see on this plot, which shows the phase of the pulsation as a function of the orbital phase. So you can imagine basically the horizontal axis as being time, and the vertical axis is the phase for the pulse. So normally you should see a trail. So basically the regular pulsation is a function of time. But you can see on the left-hand side that no pulsation is visible. So orbital phase 0.25 here is when basically the companion is at the inferior conjunction. So the companion is mostly sort of like passing in between us and the pulsar. Now, in this particular system, the inclination is not such that the companion hides the pulsar directly. There's some angle in the orbit, but still, like you can see that when it passes in front, there's an eclipse, and that's basically caused by like a giant haze of plasma that surrounds the companion and follows it. And you can even see that when the eclipses like fades away and the pulsar like sort of reappears, there's even like this sort of swing, like you can see this little kind of like hockey stick shape here. And that's basically a delay that's caused by the plasma that delays the waves. So we can actually, from the study of the eclipse, we can actually measure or get an idea of like the electron density that surrounds the star. Then if you move to the sort of near infrared and optical side, then you tend to lose the pulsar, like they're not very bright at in this band, but then what you see is the companion star. So the light is dominated by the companion star, and typically you'll see light curve variability on the orbital timescale. So you see both the flux changing, but also colors changing. And you have like a very notable example. This is basically the light curve of the first Black Widow, 1957, in a couple of like infrared bands, but also you have the R band in the optical. And you can see basically in the optical, you can see that the variability is something like 4 or 5 magnitudes. So it's huge. And it's basically created by the fact that the companion is tidally distorted. So it looks like X-shaped because it's basically filling its rush lobe, or nearly filling. And the side that's always presented to the pulsar, because the star's rotation is tidally locked, means that on the day side, as we call, the star is heated to temperatures that can reach in some systems something like 10,000 degrees. Whereas on the backside of the star, it's a brown dwarf type of object. So the temperature is more like, maybe in the low few thousand, so maybe 2000 degrees or so. And so it's this sort of like half hot and half cold star, which, as it orbits around the pulsar, you see different faces of it, and that's what causes the luminosity change and also the color change, which is also accompanied by spectral changes as well, like in the absorption lines of the star. So we can study that as well in the optical. Now, if you move up to even higher energies, so in the X-rays, there you see more like the signs of the interaction of the stars. So sometimes you do see some contribution that's from the neutron star itself. You might even see pulsations. But the notable thing that you notice in the X-rays is the sign of the bow shock. So basically the shock between the pulsar wind, which is high velocity particles that are accelerated by the magnetic field and of the pulsar, which collides with the wind of the companion star. And it basically creates this sort of bow shock that looks like a bit of a parabolic shape that either, depending on the pressure balance, may surround more like the companion star or might surround more like the pulsar, depending which of the two winds is the stronger. So you can see nice examples, like the group of Romani, for instance, at Stanford has done beautiful work, and others as well in the world on the topic. So you can see basically the, in two different systems, you can see the count rate of X-ray photons as a function of orbital phase. And you can often see this sort of like horn pattern like this. And in this one, it's a bit more noisy on the left-hand side one, but you can still see like, two peaks. And usually these are created basically as you orbit, as the companion and pulsar orbit. Eventually our line of sight essentially crosses this sort of like asymptotic, region where the where the shock, essentially the particles are accelerated along the shock and kind of like funnel away. And these are regions where you get high Lorentz factors, for instance, for the particles. And so you get enhanced emission. So that's typically what is the rough picture of it. And this enables to, do an very interesting science, such as trying to measure the geometry, of the system. Then at the highest energies that we tend to observe, so gamma rays, for instance, with the Fermi satellite, you see the neutron star again. So nearly all photons we get in the gamma rays tend to be pulsed from these systems. So there's very little. So if you look at this this example here, in the gamma rays, people tend to fold all the photons, and they show the background photons as well, but then they can estimate what the background is, and then they put a line to indicate where the background level is. So you can see here that nearly all the photons are from the pulsed emission. And in this case, you also see a sort of like a horseshoe pattern, but the folding here is done at the spin period, not at the orbital period, unlike the previous one I showed here. So here the horizontal axis is basically orbital phase, whereas here it's spin phase. Okay, so here it's folded at milliseconds. And again here the horseshoe in this case is because the emission in the gamma rays, they tend to be, we believe it's produced quite out in the upper magnetosphere, somewhere potentially connected to the what we call the outer gap, which is where basically the magnetic field lines just about close to be co-rotating within the speed of light. So that's what we call the light cylinder, and where field lines are left open. So in that region, which is called the outer gap, is probably where the photons, the particles get accelerated, and then you get the production of gamma ray photons that are observed. And so you have like a sort of like shallow emission region in a sort of like more or less like broad cone geometry. And so we probably cut across that twice, as the cone sweeps across, like on the leading edge, and then the trailing edge, which is what gives that characteristic shape. So again, there's lots of really interesting research done by groups such as that of Alice Arding, for instance. So if you remember my initial slide where I showed the number of publications as a function of time, and then things started like ramping up around like the late noughties, is because of the launch of the Fermi gamma ray observatory. And so basically Fermi has really unlocked a large number of these systems. And what happens is that, the gamma ray sky is largely populated by essentially active galaxies, which make up, the vast majority of point sources in the gamma ray sky. However, there's, among what's left is pulsars and, PWNs and supernova remnants. So early, in the early days, like a lot of energetic pulsars had been observed already in the gamma ray sky. But then there still remains about a third of the gamma ray point sources found by Fermi, where we're not quite clear what is connected to them. Because when, the localization is good, but too poor, at this sort of like arc-minute level to be able to connect, these objects to an AGN or a particular star or something else. Because of the confusion limit exists, caused by like the high density of sources visible either in the optical, radio, or else. So what people started doing is basically and that's what the Fermi pulsar collaboration, people like Paul Ray, Fernando Camilo, and like others, Scott Ransom et al. They started using radio telescope and pointed at point sources in the gamma ray sky, and then they would just sit on in the radio, and eventually some would turn out to be pulsars. And so if you just even like look at the their general statistics, you might expect maybe 1 in 20 of these sources. If there's no other kind of if the unknown sources are what we found so far, there might be 5% of them that might be radio pulsar or some sort of pulsar. And it turns out that a lot of them are energetic pulsars and turn out to be of the spider type. So if you look at, again, like at this, PP dot diagram that I displayed earlier, you can actually look at the amount of energy that's lost by the pulsar. So it's what we call the spin down luminosity. And so more like you have lines of constant energy. So the most energetic ones being near the top here. And so the crab pulsar and such, like, they would lie like at the very top in this region. And you can see in black are just the regular kind of radio pulsars. But then you can see whatever is colored is either pulsars that are pulsars that are visible as gamma ray pulsars. So either because we found radio pulsations after the fact, or we found gamma ray pulsations after the fact, or because they are, they were known before and then, they've been connected to the gamma ray source. But what you observe is that basically, the most energetic pulsars are the ones that tend to be visible in the gamma ray. And the picture is a bit more complex, but the sort of toy model is that basically pulsars tend to produce a certain fraction of the energy that they release goes as gamma rays. And that fraction might not be quite constant for all types of pulsars, but there's this sort of fiducial amount, which is probably between like a fraction of a person to like a couple of persons of the total energy they lose is dissipated as gamma rays. So therefore, the very energetic, very fast spinning pulsars are also detected as Fermi sources. It turns out that pulsars that are visible in the gamma ray sky tend to have a different spectrum to the active galaxies. So if you look at how variable the gamma ray photons you get are, and also at the spectrum in the gamma rays, it turns out that active galaxies tend to be, probably because of accretion, into the supermassive black hole, they tend to show variability, but also their spectrum tend to be much more like a power law kind of spectrum in the gamma rays. Whereas the pulsar tends to have spectra that are much more curved, and tend to be more steady. So that's what you see on this diagram here. Basically, that curvature tends to be higher for pulsars, which are displayed in red, and the active galaxies, they tend to be lower curvature, but also they tend to spin go further up, in terms of being more variable. So people have been using these characteristics to try to, pinpoint which one of the unassociated sources might be the most likely to be pulsars and go after them. And I'll show some of that a bit later in the presentation. Okay, so that's like the sort of the full introduction to spiders. Now I'll just whiz through some of the science, as I advertised at the start of the talk, that we can do with them. So the first is measuring neutron star masses. So basically, in these systems, you have a binary. The pulsar you can time using either the radio pulsations or the gamma ray pulsations. So you get dynamical information. But obviously, because all you get is the radial motion, you cannot solve completely for the parameters of the binary parameters. So the two masses and the inclination are basically unknowns. And essentially, you need two extra pieces of information to solve entirely, like the parameters. So basically, if you measure two extra sort of independent dynamical parameters, then you can solve for the two masses, and the inclination is basically just just inferred from all of this. So then the fact that you have a companion which is visible in the optical means that then you can go and look after, for instance, spectroscopy, where you can measure literally the spectral lines shifting, and then you can measure an orbital velocity for the companion, which is independent from the pulsar measurements. And therefore, you can measure more or less like the mass ratio in that way. And then you will need an extra measurement to then solve entirely. And this is what usually the light curves enable you to do. So the light curves will map the complex temperature profile on the star, but also they'll relate to the geometry. Because if you see the system face on, even if you have a half star that's hot and a half that's cold, you always see the exact same projected part of the star. Whereas if you see it edge on, then sometimes you'll see the hot face of the star, and then at other points you'll see the dark, the cold side. So the amplitude, for instance, of the variability will kind of give you a handle on the orbital inclination. So the full details are quite intricate, but we can model that, and basically there are uncertainties, but you can sort of get a bit of a constraint, for we believe for the mass, the masses in the system. So there was some early work, for instance, by Van Kerkwijk that I was involved with, where in the original Black Widow pulsar, we thought, we basically inferred that the mass might be something like 2.4 plus or minus 0.12 solar mass. This was based on like the radial velocity that we had measured, and then taking the inclination that had been inferred from the variability from an existing publication from other authors. So this is basically the little cross you have here on the mass of companion versus the mass of the pulsar, like diagram. But then if you are a bit more kind of careful about it, and then you make fewer assumptions, then you can actually infer that the minimum mass should lie, somewhere like that. This is the minimum mass you would get basically from an edge on orbit. And then the range in red here is the mass ratio that you measure. So, accounting for various uncertainties. So realistically, I mean, the pulsar, if you're very agnostic of anything about the modeling of the light curves, then the mass of the pulsar could be, spread over quite a wider range. So for instance, in the paper, we said, okay, it seems like it could be quite likely to be there, but you see if the modeling is not quite accurate, it could be a bit wider. Then others have done such measurements as well, such as Linares et al., and they got also a fairly massive pulsar mass for that particular system. The thing is that it relies on some of the the modeling of the light curves, which is quite difficult. And I've basically spent essentially since that 2011 paper, I've been working on like an improved measurement for the original Black Widow. But before claiming that the mass really is so somewhere like around 2.5 solar mass, I was really aware that I needed like some really solid proofs. And the problem with these is that it depends on systematics. For instance, the fact that the temperature profile, it's not as if we see the actual star and then you can map the temperature, because all you see is essentially the integrated light, from what's illuminated of the star as you observe it, and then it rotates. So there's quite some degeneracies. You could have something where you have like some spots, or something where the star is much more like, homogeneously heated. And depending on which assumptions you make, you may get different results. So disentangling all of that is not, necessarily that easy. And, that's why there's some uncertainties existing. Some really interesting progress has been made very lately. This is work that was led by my former, well, he was my postdoc then, but now he's got a position at the Albert Einstein Institute. Colin Clark is he's actually found gamma ray eclipses in these in a bunch of these systems. So it's a paper that's submitted. So please don't tweet about it or anything. We submitted it for publication, so hopefully it will get back soon. But basically, the eclipses that we find, like you can see here, and on the different plots, they set hard constraints on the geometry, because even though in the radio we see eclipses, that's because of the plasma, right? Essentially preventing the radio photons from traveling, just from basic plasma physics. Whereas in the gamma rays, the haze of plasma is essentially transparent to gamma ray photons. So they should not, be absorbed at all. And therefore, if you want to create gamma ray eclipses, it has to be caused by the physical surface of the companion star, literally blocking, the light from the pulsar that's behind. So therefore, it really sets, a tight constraint on the inclination of these systems. And for instance, for the original Black Widow B 1957 plus 20, it turns out that the inclination that we infer because of the gamma ray eclipses is much more a John that was modeled, from the light years before, and there's still some sort of tension actually with this modeling that we're actually trying to resolve. But if we believe that the eclipses lead to a more edge-on orbit, then the mass is probably actually somewhere just below 2 solar masses. It's probably not quite as massive that you would infer, just from optical data. So it's actually quite an interesting development. And even though, it's a bit unfortunate that maybe it seems unlikely that the original Black Widow is as massive as we thought, these constraints will definitely help getting more accurate mass measurements. The other nice progress we're making is that now we got the code and expertise such that we can model the spectrum. So here you have some nice trailed spectrum on another binary system that in a paper that's just been submitted by my former postdoc Mark Kennedy, and we're actually able to on the top at the top you basically have the actual observed spectrum from this particular Black Widow system, and then at the bottom, the lower line is the trailed spectrum. So as a function of orbital phase, you have the model spectrum. And you can see that we're able to model it really well, and this model basically should provide better estimation of the parameters in the system, because the problem is when you try to model to recover the radial velocity in these systems, the spectral lines, they change all over the place because the star is not uniformly at a uniform temperature. And therefore, you need various templates that you need to apply in different parts of the orbit. And this leads to, potential inconsistencies. And also, the light is not produced always at the same location on the star. So if light comes from the inner part of the star, it's going to have a lower velocity than the actual center of mass. So this should account for all of that. So hopefully, we should be able to, populate essentially the population of masses, by doing such measurements. Some have been done, in the past. So this is the old measurement from 1957, which will probably be moved further down. And then there's been some very solid measurements, done in the past. The 0348 measurement is actually, what John Antoniadis had done a couple of years back. But that was not on a spider system. That was with a white dwarf system where a lot of these intricacies, they go away. So you can go and do much more accurate, modeling. And also in other systems, you can also measure relativistic effects. So they're kind of a pure dynamical effect. So these other measurements that are quite narrow in mass uncertainty, they basically correspond to very solid like dynamical measurements usually. So so they're quite reliable. Whereas the ones for the spiders, they're a bit more up in the air at the moment. But still, if we can do it for a large population, that's still interesting because it teaches us a lot about the mass and how pulsars might accrete matter over time. So that's quite important because basically if you see on this mass versus radius for neutron stars, various lines there are essentially different equations of state, that describe the internal structure of those stars. And we basically just don't know which one is the right one. So if you can somehow measure high masses, then you're able to exclude some of the equation of states. And so, for instance, from the work of John in the past, you can more or less exclude like a lot of the models where we call like the soft equation of states, where you have a fairly strong mass radius. The radius changes quite strongly as a function of mass, whereas the ones that seem to be the most likely are the ones that predict higher masses, and they're stiff equation of states where basically the radius varies very little as a function of mass. Yeah, so that's one of the areas. Then we can also study binary evolution. So in the sort of typical systems, binary pulsar systems that we knew of that had white dwarf as companions, these typically are what we call diverging systems. So basically in these systems, what you have is you have and it's easily pictured with this diagram where you have the orbital period of the binary system as a function of the mass of the companion. And then basically if you have like, different stars in different orbital periods, but they all have roughly the same mass initially, and then they start transferring mass, at the end of the day, they will end up in white dwarf, and then there's no more mass transfer. And when this takes place, then there's no longer evolution in this system. So they kind of like get frozen in somewhere. And there's a pretty strong correlation between the orbital period and the final mass of the companion star. And that's caused by the way binary evolution works. And that has been observed. So I'll just skip over. I can get back to that later, but I just want to make sure I finish my talk on time. So there's quite a strong correlation that's been predicted. And mass measurements, basically, that one is from an older paper, but we could update it with like more recent mass measurements of these white dwarf companions. It fits really well, the prediction. But in these systems, the orbit widens because basically mass transfer from a small companion to a heavier companion tends to widen the orbit naturally. Now, if the orbit is very tight initially, so beyond a certain threshold, then the mass transfer takes place earlier on in the binary evolution, when the star is more or less on the main sequence rather than the point where it reaches the giant branch. And at this stage, because the orbit is more compact, there's actually an effect that we call magnetic braking, which is dominating over the mass transfer effect for angular momentum changes in the system. And that coupling basically of the magnetic field with the wind of the pulsar basically slows down the companion, and then it will actually gain angular momentum and it accelerates the companion, gains angular momentum, and the orbit tightens. And so you have essentially orbits that converge for these. And so along the track, more or less, you have like the area where we find the redbacks at a couple of tenths of solar masses. And then the black widows are further to the left at a few hundredths of solar masses. And these sort of like just regular tracks, they can't quite explain directly how the evolution takes place because there's extra ingredients actually taking place. You need to add the fact that the companion also evaporates. And because the companion evaporates, it really enhances the widening of the orbit at that stage. And so this causes like the evolution to then like shoot up on this diagram and the orbits to widen fairly quickly when the companion evaporates. And yeah, so we have the black widows and the redbacks. And as you can see, I mean, these are just like statistical values basically for the masses, but there seems to be a bit of fewer systems basically right in the middle. So that's why like there's these two classes, black widows and redbacks, and we're not quite sure if one turns into the other or if they're like two different types of populations from the sort of same kind of underlying evolution. And so there's different school of thoughts, like, you know, for instance, Chen and Torres and others believe that they don't turn into one another. Whereas like, you know, for instance, the Argentinian group of Benvenuto, they believe that maybe like there's an evolution of one into the other. So it's still a very active research area. But something also that's really interesting about the evolution of these systems is that, you know, as I described earlier on, we believe that these fast spinning pulsars are the result of recycling, whereby, you know, in the past you had an accretion disk that carried angular momentum and spun up the pulsar to really fast rotation. So when the companion, you know, ends up its life as a white dwarf, for instance, then there's no further mass transfer, and then the system should be frozen into having, you know, just a pulsar and a white dwarf or some, you know, other type of companion. And so this is the evolution that people thought, you know, was happening like for a long time, and which was more or less confirmed with the discovery of the first redback, PSR J1023, by Anne Archibald, which was published in 2009, where they basically found a radio pulsar. And that radio pulsar was known a couple years back to be not a radio pulsar, not emit pulsations, but it had an accretion disk. So it was basically an active accretor, more like an X-ray binary, and then it became a radio pulsar. Now, the twist in the story is that a few years later, the same system, 1023, was seen in 2012, or 13 rather, to disappear, and then an accretion disk reappeared. So it seems that, you know, in this evolution from X-ray binaries producing millisecond pulsars, there seems to be potentially a stage in the evolution where actually the system can kind of be a bit undecided and flip-flop between like an accreting systems with a disk and just a diskless system that's like a pulsar with a companion. So so it's been, you know, flopping back to the sort of X-ray binary state. And then there are two other systems that have been observed to do the same, one in the globular cluster and another one in the galactic field, which have been seen to transition from one to the other to back to the other. And M28 in particular, over about like 1 or 2 decades, has been doing this cycle like a couple of times. So it's really interesting, you know, for binary evolution, and also it gives like opportunities to study like how this accretion disk is building up from nothing and then how it vanishes. So on this plot, you can see basically, you know, a plot from the Stappers et al. Paper where they announced that 1023 had disappeared. So you can see time running on the horizontal axis. And then here on the vertical axis is orbital phase. And you have a range like from between the two red lines. That's like the range where the companion is at the front and where you have eclipses. So the pulsar was never observed basically in that range. So that's why you have like crosses, which means non-detections. But then outside of it, you have circles. And the size of the circle was basically proportional to the signal to noise, which basically because all the data were observed with the same setup, it was basically like how bright the pulsar was. So you would get like some variability, but essentially it was always detected. And then at some point in 2013, you can see the pulsar was detected. So we kind of like just zoom in, you know, the last part. And then the pulsar was detected. And then eventually it was not detected anymore where it used to be detected. And then we excluding myself actually, but people at Jodho Bank intensified the follow-up. And then the pulsar was nowhere to be found. And then they just like stared at it like forever. And then it was just gone. So this was the transition. and it's happened else, in these other systems. And when it took place, there were observations, for instance, by Swift, kind of like happening to be observing in this region of the sky. And then you can see the flux essentially like jumped by a factor of a few in the X-rays when the pulsar disappeared. And basically, the jump in flux is the change from like just the bow shock, the interbinary shock, to like having essentially an accretion disk now emitting light as well in the X-rays. So 1023 has been studied extensively in the last decade, for instance, since that, phase transition. And there's been very nice work, for instance, from Bogdanov et al. Shabazz as well has done some nice work. So the top light curve is basically in the X-rays, and you can see essentially the pulsar, well, the light from the system essentially flip-flopping between kind of like two very different states, one that people call the low state and one that people call the high state. And they last essentially like a couple of minutes to a couple of hours. And then sometimes you also have like these flares. And then it was also found that in the optical, you have like this similar thing going on. So you still see a bit the companion in the optical, but then about half of the flux in the optical, since the disk has reappeared, comes from the disk and all the the other matter, and not just from the companion surface itself. And you also see like this sort of like modality going on, and even some sort of flares. So the picture basically, and there's a nice paper on the archive right now by Giodan, which summarizes well, is that probably that in the low state, the accretion disk just sort of like the inner edge of the accretion disk just expands a bit, just beyond either the light cylinder or the innermost stable orbit. And it's such that basically the system is in what we call a propeller state, whereby the matter in the accretion disk basically just is flung out of the system in a sort of jet. And then sometimes when the ram pressure increases, then the disk inner boundary goes just a bit, closer in, and then it's basically possible for like some sort of accretion streams to, funnel towards the neutron star. And so that's probably what explains like this bimodality. There was also like some nice Kepler data, basically something like 2 full months of coverage, uninterrupted on 1023. And Kennedy, who's in my group, as part of my group, we did like a nice study of these fluctuation and flares actually. And what we found is that the flares, they basically tend to organize, the waiting time between the flares and also their amplitude. They tend to organize what we call like self-organized critically. So a bit like avalanches or earthquakes or solar flares. So it seems that there's a bit of one of these sort of like criticality feedback system that takes place where things build up, and then the larger energy release, then the more you have to wait until something else takes place. And I think it fits basically that picture that Giodan has summarized in her latest paper. The system is seen also to pulsate in the X-rays, but only in a particular state of the pulsar, where basically you're in the high state, and then potentially accretion takes place, and that seems to be where pulsations are taking place. But also the pulsar, because of these pulsations, can still be timed using the X-ray data. And it's found that basically the pulsar is still spinning down. So even though some mass might be transferred onto the neutron star, it seems that the accretion rate is the actual accreted mass, on the pulsar is still too low to actually prevent it, to actually make it, spin up. So it's still spinning down overall. Also, optical pulsations have been discovered. So at high speed photometry, the Italian group of Ambrosino et al., like they found these nice pulsations. And then more recently, UV pulsations were also found from HSC and HMM data by Giodan et al. And it seems that the accretion process is not intense enough, as I said, so that it's actual a hotspot or something like more typical of like typical accreting X-ray pulsar that produces them, but rather it has to be something more like, a magnetospheric effect, like some sort of synchrotron emission that produces these pulsations. There's also other systems. There was a nice paper again from my group on a system that shows this sort of like flickering and bimodality, and even eclipses where we can put constraints on the mass of the system, and it really looks like one of these transitional millisecond pulsar, except that the system has only been seen with like in the disk state so far. So presumably one day it might transition and become a radio pulsar. And there's a bunch of them out there. So there's lots of really nice work, for instance, by the group of Jay Strader as well, and other groups in the world who have found a couple of these systems that look like they can be transitional millisecond pulsars. All right, so I think I'm nearing the end of this topic. I'll just say a few words on timing, and I'll try to conclude fairly soon. But these spider systems, many of them, even though they contain a millisecond pulsar, which normally are the great, pulsars you use for timing and efforts like pulsar timing arrays, it turns out that a lot of these binary, spiders have orbits that are rather chaotic. So if you look at, one of these particular systems that my former postdoc Colin Clark has worked on, and also one of his former PhD student, Plex, his former PhD supervisor rather, they managed to fold the data over like a sort of 10-year span from the Fermi data and get nice pulsations. But this, in order to do this, they had to basically shift the orbit over time, so that the plot that you see on the left is basically the change in orbital period compared to the current period, so the fractional change in orbital period. And you can see, it's very tiny changes. We're talking about like a 10 to the -7 effect, right? So they're changes of like fractions of second in orbital period, but they change, and they would otherwise accumulate over time. And so Colin has devised this really clever technique using Gaussian process modeling, where the orbital period is allowed to essentially change over time very smoothly and very gradually. And essentially, it seems that the orbit is a bit like kind of unstable. Now, this was explained a bit better more recently by another postdoc a former postdoc of mine, Guillaume Voisin, where basically he studied on the theoretical basis, the case of the orbital dynamics of a pulsar having a star that is tidally that is close to filling its Roche lobe and in a near circular orbit. So using a near circular orbit approximation, but expanding essentially like the post-Keplerian formalism, what he found is that in these systems, there might be a small eccentricity from the orbit being eccentric, but even if all of the regular eccentricity was to go down due to tidal circularization, there should always remain a minimum eccentricity in these systems beyond the Keplerian part. And so because the orbit should always remain a little bit eccentric, and that's caused basically by the tidal deformation of the star. This means that on top of a typical relativistic precession of the orbit that is just naturally occurring and that we observe in more eccentric systems, or even in fairly circular systems like the one that John Antoniadis observed in the past and did like some beautiful tests of relativity with them. There's also a precession that's induced by what we call the static tidal part, and also another one that is called by the tidal, more like the time variable tidal part. And so there's some beautiful data spanning like basically over 20 years for this particular Black Widow J2051. And people, for instance, based in Bonn, like Scheffler et al., they measure quite some variability in the system. So the orbital period, like changing over time, and then the ascending node position changing over time. And they are just like measured essentially the timing kind of piecewise to try and characterize this variability. But then in a second paper, basically, Guillaume Voisin has managed to essentially include it in a more like self-consistent way with his like timing model. And we could measure basically a precession of the system and a small eccentricity for the binary. And then from that, we can more or less measure the quadrupole moment of the companion star. And even to some extent get a handle on the internal structure of that star. So it's quite exciting stuff, and which we're hoping to pursue in the future. I'll skip over that. I just want to show a thing or two about the radio eclipses. So there's been quite a lot of work in the past, but I had a PhD student whose thesis was solely on the radio eclipses. And we use LOFAR, which is an interferometer at low frequency. And LOFAR has this capability of taking, the high time resolution observations that we normally do take for pulsars. So it's basically just no imaging. It's just time series analysis where you measure the pulsations. And then normally you lose the pulsations, as I've showed in that earlier slide. But on top of it, LOFAR is able to do interferometric imaging. So you can produce an image and you can see the image of the pulsar as a function of different orbital phase. And phase 0.25 is basically when that companion star is at inferior conjunction. So you can also see in the images that the pulsar is disappearing. And it's quite important because it could be that the eclipse mechanism would have been something like scattering, where basically it just dilutes, it spreads the pulsations over a wider time, and then basically it just blurs the pulsations, but the photons, they still get to you. It's just that they're not all bunched into a nice clean pulse. But the fact that it disappears in the optical data means that, not the optical, but the imaging data, means that the photons are actually completely absorbed. And so it looks like the eclipsing mechanism is synchrotron absorption. But the other thing, and that's what you see in this plot here, is that in blue, you have like essentially the average light year from the pulsed data. And sorry, I think it's in the next slide rather. In blue, you have the pulsed data, but then in yellow or orange, you have the imaging data. And it turns out that the pulsar reappears in the image earlier at the end of the eclipse than the pulsations reappear. So there is a zone in essentially that haze of plasma where the plasma becomes transparent again to the propagation of radio photons, but where the medium is still very turbulent and essentially scatters the pulsations, but the photons still get to us. So there are, in fact, two mechanisms for the eclipses. So we have a bit of a way to study, the surrounding of the star. So I'll skip over these things. And finally, I just want to mention also that in these systems, the optical light from the companion, it tends to be very asymmetric in some systems, which means that you don't have like just direct heating, from the pulsar wind that illuminates basically half of the star and the other half being cold, but rather that some of the heating is either asymmetric in origin or that some heat gets redistributed. And there are various models for that. Romani et al., like for instance, I've put together some really nice explanations. One is that the heating actually comes from reprocessed photon in the interbinary shock. And this binary shock might actually not be quite symmetrical because of the motion of the companion in its orbit. It might essentially kind of skew a bit the shape of this binary shock, and therefore it might produce some sort of asymmetry in the light curve. Another scenario is that the magnetic field of the companion might funnel some of the, say, electrons that cause the irradiation and might cause some sort of hotspot or asymmetry on the surface directly. Then there's another, so we see, these sort of asymmetries, like very obvious in some systems. And yeah, we've done some work on that as well. But I just want to jump here where basically my group and Romani's group lately also looked at diffusion effect, where basically the heat can start redistributing towards the back just from natural diffusion, but also where the companion can have like essentially convection driving some sort of like flow on the surface, a bit like what is seen in Jupiter or also in hot, exoplanets, where you have like a stream of hot gas, often along the equator, that drives a current and can carry heat towards the back, but will preferentially, carry it in the direction of that sort of jet. So that can also create asymmetries. So it's a very hot topic at the moment. Yeah, so as you can see, there's a lot of like, sort of like physics, that we can do in situ in these systems. And there's quite a lot, coming up. In the last year or so, we started through the TRAPOM project at Meerkat. We've been conducting a survey to find more of these pulsars, like using the same principle of like staring at these Fermi sources and trying to find radio pulsations. And Meerkat is, this beautiful array of 64 dishes. And it's, the most sensitive telescope in the southern hemisphere. And we already found like, a big bunch of new pulsars. So we have a publication in preparation. But we found like something like 10 new pulsars, and basically all of them are millisecond pulsars, and many of them are binary systems even. So yeah, so there's more coming. And yeah, thanks for attention. I'll stop here and maybe take some questions.
Many thanks, Rene. That was very, very interesting. Are there any questions for our speaker? Let's just speak up or raise your hand or whatever. Or maybe, I have quite a few questions, but maybe I can start with one. So I was wondering about 1957.
Yeah.
And it was actually very nice to see this, that you see these eclipses in the gamma rays. But do you have any ideas of what might be causing this discrepancy in the inclination that you get from the optical light curve?
Yeah, not really in a way. So we, and that's why, like in 2011, when we published the initial, when the paper that Martin, was leading, we did the sort of traditional approach, which was to, cross-correlate like the spectrum, get the velocity, and then we did some corrections to it to kind of get the correction from where the light comes from at the inner side to the barycenter. And then we just used the optical modeling from what was published. And then I started, I had like, data and stuff, new data. So I started modeling it. And yeah, the modeling, essentially the modeling would tend to be a bit inconsistent. And then I was quite worried, that was something a bit weird going on. So that's why I kept holding on. And then I thought that if I was able to produce, these nice sort of like fully consistent spectral modeling, that it would solve the problem, because basically there were inconsistencies between the spectroscopy and between the photometry. But now we're able to do it. Like, so we solve all the problems, and in the last sort of year, we have like a code that works, and we've modeled, like that's another system, what you see, but we've modeled also 1957. We're hoping that within maybe 2 months or so, we can submit the paper, but we still see inconsistencies as well. And
right.
The optical data wants an orbit that is more like a bit more face on, in the sort of like mid 60 degrees orbital inclination, whereas the gamma ray eclipses favor something more like, closer to like edge on, 80 degrees or more. And it's not quite clear why. Now, I mean, the thing we're now exploring is basically we're just probably going to take the kind of orbital constraint from the gamma ray eclipses at face value and assume it's right, and force that to then try and like model the temperature, like see if it's possible to get some temperature distribution on the surface that would enable to fit the data, basically. But basically, so far, like the more like first principled approach, where we have a model for even for asymmetry, because 1957 shows asymmetries as well. Like they're very tiny, but we have now like beautiful data where, you know, we at sort of like centi-magnitude, you know, precision, and we see some small asymmetries. And even with these models, you know, like diffusion or the, you know, the sort of IBS, you know, from Romani, we still see, you know, it still doesn't work. You know, it doesn't want, like, you know, to reproduce the gamma ray, you know, inclination. So I think we'll try to do the other approach. We'll just take the inclination, and then we'll see if we can just, you know, essentially construct a temperature profile on the star that might match it. So I think that's going to be probably illuminating us, you know, in terms of what it looks like, or it might look like, and then try to understand then what sort of physical process might be causing that. Yeah, so that's a bit of a word of caution, basically, with all the optical modeling, is that, you know, there are systems like this system, for instance, the one I'm showing is J1555. That one, there's also an eclipse for that one, and basically it's an agreement with the optical modeling, so it works. But then in some other cases, it doesn't quite work. So there might, you know, there's something obviously we don't understand.
Yeah, that's very interesting. And is the phase folded optical light curve constant over time?
Well, as far as we can measure it, yes, but yeah, I mean, the problem is that, yeah, these studies, right? I mean, say the original Black Widow, 1957, the orbit is 9 hours. So it's, you know, so it's basically a full night, you know, and often, you know, you have to break it up in a couple nights. And then, so it's quite demanding projects, you know, to really like measure it all and like do it over and over again. And they tend to be faint as well. So yeah, we're trying to do this on brighter systems. But yeah, we're not quite there yet that we have like enough data, I think, to really tell like for sure. But, you know, in some systems, so I kind of like didn't enter into the details, but there's that system. I keep forgetting. Sorry, I should have put the name, but it's from Collins' paper from 2020. So I think it's 0427, the name of the source. And in that one, we got like 3 different epochs, and you can see like you know, like in this case, we see 2 peaks per orbit, and that's due to the ellipsoidal, you know, there's some irradiation. That's why like this and this are not at the same height, but it's a redback, and the primary modulation is actually from the ellipsoidal shape of the star. And then you can see actually that the ratio between the sort of left and right one is changing, you know, from one year to another.
That's very similar to what we saw in another redback called 1723, where you also see
and actually, you know, I apologize for not mentioning your work. That's the one with the where you found like these the spots, right, and that the star is not exactly co-rotating, isn't it?
Yeah, the thing is that it's not only dark spots, apparently. I mean, if you know, believe the spot interpretation, you also need the hot spots to explain what you see. So yeah,
exactly. Yeah, sorry, I didn't mention because I had like, you know, an immense amount of material, but yeah, so
no, but it's very interesting.
Yeah, it shows, yeah, like, you know, there might be spots and stuff, but then, you know, like in this one in particular, right? I mean, the spots would have to be exactly like right at the place where you see the star from the side. You know, it seems very weird. And then, so I think there's still a lot of mystery, but it could be. And there's another system as well, like called 2129, for instance, where we don't necessarily see what you're talking about, like where the phasing and the optical might change over time, but rather like there's a secular change in the brightness of the system over time. But, you know, we're talking about like a few hundreds of magnitudes, but it's very detectable because it's a bright, you know, it's a bright redback, a bit like, you know, a bit like yours that you studied. And again, like, so it means that, yeah, there's some, you know, the heating or things like that are changing over time. But if you just extrapolate, right, from the work of Scheffler, for instance, or Voisin, where the orbit, you know, is variable over time, you know, here, the amount of change in the orbit is too small in the optical to be measurable, you know, in a very, I mean, you would need to spend a lot of time on a really big telescope to get many orbits to maybe measure that. But it's, you know, we're talking about like kind of a second time scale. So yeah, so I'm not sure that in the optical we would see these orbital variations, like in terms of pure dynamics. Now, if you have things like, yeah, like, you know, spots and things, then you might see changes, but that is different from the pure dynamics.
Interesting. Okay, I think we're running out of time, but maybe there's time for one short question. 3, 2, 1. No. So if not, let's thank Rene again. So thanks again for this, you know, extremely interesting talk, and hopefully next time we can repeat it in person.
Yeah.
Okay. So thanks, Rene, and bye. Talk to you soon.
Thanks everyone.